Okay, so welcome back everyone to the joint Minds Ideas Symposium. Um, it is my great honor to introduce our next plenary speaker, Sham Kakade. Sham is a professor of computer science and statistics at the University of Washington, focusing on the foundations of machine learning and artificial intelligence. Sham is world renowned for his numerous fundamental contributions to reinforcement learning, bandit learning, spectral learning, non-convex optimization, and representation learning, to name a few. Many advances in these areas resulting directly from Sham's work have really helped shape modern machine learning. Um, and for his contributions in ML, Sham has received several awards, including this year's ICML Test of Time Award, but also IBM Pat Goldberg Best Paper Award in 2007 and Inform's Revenue Management and Pricing Prize in 2014. Sham is truly a leader in machine learning education. His course notes on computational learning theory were the go-to resource for many of us when there weren't many texts on that topic. And over the years, Sham has organized tutorials on various topics and at major conferences, including a tutorial on reinforcement learning at the upcoming NeurIPS. I know, has a monograph in preparation with an early draft available on his webpage on foundations of reinforcement learning, which is what he's going to talk about today. And it's needless to say, really, that he has been instrumental in training a new generation of ML faculty and researchers. At University of Washington, Sham co-leads Tripod's Institute on Theoretical Foundations of Data Science and recently launched AI Research Institute in partnership with UT Austin. Prior to joining University of Washington, Sham has held appointments at the University of Pennsylvania, the Toyota Technological Institute at Chicago, Microsoft Research, New England. Sham was one of the first graduates of the neuroscience program at the Gatsby unit at University College London. His PhD thesis really laid the theoretical foundations of reinforcement learning. And he has continued to lead the development of this relatively young but critical area of machine learning. And today he'll tell us about some of his recent work on fundamental statistical limits of batch reinforcement learning. Very pleased to have you, Sham. Over to you.
Thanks very much. Thanks for the wonderful intro, and thanks for setting up this event and hosting me. I'm really excited to talk about some questions today with regards to offline reinforcement learning. It's pretty new work. Definitely feel free to ask questions during the talk. So, we clearly are seeing a lot of advancements in reinforcement learning. It's becoming one of the dominant, or it has been for a while, like one of the dominant paradigms for AI. But there's good reason to believe it's going to have a more pronounced impact on science and technology. One of the things that maybe relatively recently has been seeing a lot more interest is this area of offline reinforcement learning. So online reinforcement learning is the usual setting where we interact with some environment, we get data, and we try to improve our behavioral policy to optimize some measure of long-term future reward. This offline paradigm is just the fact that, look, in many settings, we actually have a lot of data available to us. It's often, observational data, but we'd like to somehow utilize this data to come up with a sequential decision-making strategy. Okay, so this is really a question about data reuse when we have offline data. And it's clear, like in many very realistic applications. So think of like healthcare. We have like a ton of electronic medical records, and we'd actually like to use these records to do something non-trivial with regards to actually a sequence of making a sequence of decisions based on the current state of the world. Okay, so this is a pretty influential paper on some of the challenges in this space. Let's go through quickly some of the challenges we face. So we have the problem of sequential decision making because our problem is 8 steps, and the decisions we make now will impact the future because they're state in the world. It's not an IID world. In this setting, more often than not, we aren't really running causal experiments. Our data is just observational data collected in some manner. It might not be balanced enough for certain groups. There might be various biases and so on. On top of all of this, we have the problem, we have the cursive dimensionality problem, which is, the covariates of everyone, if we start taking combinations of them, it's effectively infinite, like everyone's different. Okay, and we need some way of dealing with this kind of large state space. So when I say state, think of like the person's features and possibly a very large number of treatments. Okay, this is like a binary tree, but you can easily imagine like cocktails of drugs at every stage in this game. So somehow we need to use some way of doing function approximation or regression or supervised learning to deal with this latter challenge. And that of course makes the top two even more challenging. So I'm gonna keep this running example of coming from healthcare because it's a little more compelling than the usual sponsored search types of examples. And it's something people are taking very seriously right now. Okay, and before jumping into things, let's get some intuition as to when this might work. Because people are trying this now and they're aware of various challenges with regards to, say, just mathematical basics. Let's just get on the same page and see when we can agree that some kind of offline reinforcement learning will actually work. So again, think of this electronic medical records setting. Let's make life easy and forget about the sequential decision-making aspect, but let's focus on the cursive dimensionality. So we're going to consider a horizon 1 setting where we see some input state S. We're going to choose some action like a treatment, and we're going to get some reward back, which is the quality of the outcome. Think of this as real valued, like how long it takes the patient to get better or various other real valued measures of quality. Okay, so S is the state. It's basically infinite. It's all the patient characteristics, combinations of them, what other information we have. Our action will denote by A. We want to know how well, okay, so this is our setting. There's no sequential decision making. It might be a sequence in that we might be playing this game over and over, but there's there's no state to the sequential decision making problem. Like we might play it over and over again, but the next time we play it, we aren't necessarily thinking of the decisions we made at time step 1 changing the world. Okay, so this is why I'm really simplifying things to look at an H=1 case, and I want to understand when we can do this. Okay, so there's 2 conditions if you think about this as to when this will work. Okay, so suppose we have a linear model with features. So our features phi are in R to the D, and we think about this as much smaller than like the covariates and all the combinations of them in our data set. Okay, and let's suppose for a moment that this linear model is correct. This is a very strong assumption, but let's suppose it's correct. Okay, then we know that basically if our data set has coverage over the features, we'll fit the linear model and we'll do very well at predicting an outcome for any new test point. Like we don't need any distribution at all. So when does this work? Okay, so we get some offline data set. It's triples now. It's the state of the world, the treatment we took, and the quality of the outcome. Define sigma to be just our data set's feature covariance matrix. Okay, and we know that so when is this going to work? Like let's just make the very strong assumption that our linear model is correct. Okay, and let's make the assumption that this data covariance matrix is well conditioned, because obviously if we don't see certain directions in our data, we're not going to be able to estimate the weights well, and we will not learn this model. Yeah, but if it's the case that this minimal eigenvalue isn't too small, the features are bounded, we'll have a well-conditioned matrix. We're in great shape. But what's very nice here, since the model is correct, we'll actually be able to predict well on any new person action pair. Because again, it's a strong assumption here, but there's no problem with using offline data when our model is correct and we have coverage. Because we get any new person, we know the model, we know exactly what to do, and a relatively mild sample size. It depends on the target accuracy, the dimension, the minimal eigenvalue. We get a wonderfully strong guarantee here with these strong assumptions. Okay, so that's the H=1 case. Okay, now let's move to a simple case with H bigger than 1, so we can again get on the same page and try to see what people do in practice and what are the challenges. So now let's go to the sequential decision-making problem and look at this super toy example where there's 3 states in the world. Our car is either cool or warm, or we've driven too fast and it's overheated. There's 2 actions, which is fast and slow, and our reward is, over some H stage game, we'd like to obtain a lot of reward. Okay, so it's a very simple game, and there's some stochastic dynamics. So in some state S, we take some action A. There's a transition model over the next state distribution. Let's suppose all the rewards are bounded in -1 to 1. Okay, and let's think about the offline setting. So we have this offline data set. Okay, so note now our offline data set is has 4 things in it. It has the state we took, the action we took, the next state we get to, and the immediate reward we obtained. Okay, so it's got these transition triples and the reward outcomes. Okay, and our goal is to let's just make life easy. Forget about even improvement. Let's make life super easy and just ask the question of, can we evaluate a given policy with an offline data set? Okay, so this is the policy evaluation question. Much easier than improvement. If we had online data, we just run the policy, we're done. Okay, so in this very simple setting, it's pretty, looks like my lemma disappeared. Okay. It looks like I had a lemma here that vanished, but in this offline setting, it's pretty easy to convince yourself that if you have a lot of data for every SA pair, you learn a model of the world and you're done, right? So if your data set has coverage, basically like poly 1/epsilon samples at every state action pair and poly H samples, you're going to be able to evaluate any policy, because at that point, you've got a very accurate model of the world, and we're done. Okay, so in this case, we're very easy, but of course, what's the problem here? We haven't had to deal with the curse of dimensionality because the true states in the world, there's only 3 of them. Okay, but let's just go through what the procedure is to estimate the value of a policy. So this is a bit of a more general audience slide here to get you up to speed with just this algorithm Q iteration, which is pretty widely used. So we have our offline data set, and we're going to, and the semantics are S prime is the next state we got to, and let's see how we're going to evaluate a policy, an H-step policy. Okay, so at the last stage, we're going to define this Q hat value, which is our estimated reward had we took action A in state S. Okay, and I'm fixing a policy pi here. Okay, then I'm going to go backwards. I'm going to look at the value at the last state, which is going to be the Q value for the action we took. Okay, so now I'm relating the Q to the values V at the very last step. Okay, which is I just plug in the action I took, then I know the value of my policy at the last stage in the game. Okay, now I can proceed going backwards because I go backward to step H-1. I look at my immediate reward, and then I add in the value I get under where I go to, and I just use my empirical data to estimate this. Okay, so now is my lemma that, look, when does this work? As long as this offline data set of endpoints, as long as I have like poly 1/epsilon samples at every state action pair, I've got an epsilon accurate in my estimate of this value, which is this H stage value from the start of the game. Okay, so everything's great. This is kind of easy to do when the number of states are small. Okay, and we kind of know we have these Markov dynamics. Okay, so let's actually see what we might hope to do in practice now in a setting like this. So this is the tree, which is all the possible outcomes. Like we don't necessarily see all of these outcomes because it's 2 to the H possible treatments in this binary setting, and these treatments we can apply in a state-dependent manner, right? Because we can make the next decision based on what we've done in the past. Okay, and what's the obvious thing we're going to do? We're just going to try to run this algorithm with some type of approximation at each step. And the hope is, for this offline problem, can we somehow avoid this exponential blowup, or even the online problem too? Okay, so we're going to have some features just like a regression, because that's what avoids the curse of dimensionality. we know, just like regression, it's pretty reasonable to hope that we have some kind of coverage over the features. So basically, at every slice in this game, we hope to have coverage. And and under two assumptions like this, we know at this last stage we'll be okay by a regression guarantee. So as long as this last stage we have coverage, not seeing all 2 to the h leaves, but we have coverage in our feature space, regression will be fine. Okay, and then the hope is we're going to take the outcome of regression, plug that in to level h-1 and proceed, and we like this to work. Okay, and this is a widely used algorithm. So this is this fitted Q iteration. You could call this least squares policy evaluation. So we take our data set of endpoints, and we're going to go backwards. What are we going to do? We're just going to straight up use ordinary least squares. We just do regression. We use a plugin estimate, and we go backwards. So at the last stage, we approximate our reward with, we just do a regression, get some W hat H, we figure out a policy, figure out the value, which is just, look and see what happens based on the policy we took at the last stage, plug that in, redo the regression. But this is the key step here, that when we go back to h-1, since we can't run our policy, what we're going to do is use the plugin estimate we got at level H. And if we had coverage, we know uniformly we have we have a very accurate value estimate at level H, and we're going to go backwards. Okay, and the hope now is maybe under conditions like this, we can actually do offline policy evaluation and address this kind of problem of cursive dimensionality, sequential decision-making issues, and the sampling biases, as long as we have coverage. Okay, so the rest of the talk is really going to be trying to get a sense of like what are the statistical limits of data reuse with function approximation. See, without function approximation, everything's pretty straightforward. Okay, but to really have successful impact, we need to bring in function approximation. So let's limit to regression, because this is one of the most widely used tools. And if we can't even understand this right, going to deep learning and such makes no sense. So this talk is really going to be looking at necessary distributional and representational conditions which permit sample efficient offline reinforcement learning. And let's focus on policy evaluation, which is the best case scenario. And we're going to make strong assumptions here. Okay, so the possibly surprising thing here is, in this best case scenario, we're going to see that when our linear model is correct in a very strong sense, so this is what on the machine learning theory side we call a realizable assumption, but we're not going to assume there's like model misspecification. And we're going to assume coverage in this regression sense, like a certain spectral domination sense. And we're going to see this is actually not enough. And this is a bit surprising to many of us, and we'll discuss implications of this. Time permitting, I'll get at upper bounds, but I think the implications of this are more important, and I'll spend some time discussing that. Okay, so we're really trying to pin down, does this work? Because this is kind of the most natural thing you would try in practice. Like regression is what we always do on observational data. It's one of the common tools. Assume the regression model is correct. Will we be able to estimate the value of a given policy? So forget about even improving this thing. We just want to do policy evaluation. And like, what are the statistical limits of doing this? Okay, so we'll just quickly go through the setting and definitely ask questions about the setup, because I've tried to at least give you the intuition of what's going on if you haven't seen the details of the RL setting. So is there a question?
Yeah. I have a quick question, Sham.
Yeah.
So we're not making any assumption here regarding some importance sampling with respect to the data collection policy in these.
Yeah, right. Great question. So, right. So one of the, so someone's asking, like, are we doing some kind of important sampling tricks for a data collection policy? And the hope is like, maybe this will give us coverage. And let me come back to that a moment, because I gave one algorithm, which is pretty common. Another procedure is using importance sampling. Okay, so we're going to ask this question, so there's really two common tricks here. Like, we either do backups or we try to do importance sampling, which is usually used in conjunction with backups. Okay, and while I phrased this for intuition purposes as using this LSPE algorithm, this lower bound is going to be information theoretic. So we can do anything we want. Okay, so hold that that question for a moment. I'll mention important sampling in a moment. Okay, so let's do you have anything else? Okay, so let's quickly just set up the assumptions. And again, like I feel like I'm hoping that this is reasonably accessible, even if you aren't an expert in RL, because just think of this as a state-based setting and we're trying to do backward induction. Okay, so the setting is that we're going to have some data, a sequence of data collection distributions, and think of these data collection distributions as just giving us an IID samples of SA, S prime, where S prime is the next state under the true underlying dynamics in the world, and we get a reward. And we're going to get some nice IID data set from mu1 to mu8. So this is somehow only easier than having correlations in the data. Again, let's suppose we know these distributions mu. Okay, so we know these distributions. We have access to some way of collecting data, and just so we're on the same page, this state action value, which is helpful in this backward induction procedure, is something that, so it's a function of h and pi. So fixed pi, what this is, as at some state, if we take an action A, then we follow pi for the duration of the rest of the game. So we're starting at sh equals h, we take ah equals a, then we follow the policy till the end of the game. This q pi h is our expected reward. Okay, and this is a very handy thing to compute to do backward induction, right? Because this backward induction is we compute this thing at the last stage h, and then we go backwards. Okay, so now let's just make our two assumptions and see what goes on for this, this lower bound. Okay, so the first assumption is that we're going to make a pretty strong assumption on these state action values. So we know our feature map. Think of this feature map, like in practice, we're going to make this feature map to be much smaller than the number of possible states and actions. Okay. Sometimes our actions are small, but in many cases they're pretty big. Okay, so our first assumption here is this realizability assumption. And we're actually going to make a somewhat strong realizability assumption here, which is these features are good in the sense that for every policy, the state action value can be perfectly represented as a linear function of these features. Okay, so not just not just the policy in question that we want to evaluate. Let's just suppose every policy we might ever want to evaluate can be perfectly approximated with these features. Right, so at h equals 1, this is literally just the regression assumption is true. Okay, but this is, stronger in the sense that there are possibly, exponential number of policies. Like if it was a binary tree, it's 2 to the h policies. And for every one of them, and at every stage in the game, we're going to assume our features can perfectly represent the state action value. So it is a non-trivially strong constraint. Okay, so now let's go to the next question of coverage, because even at h equals 1, right, if we're missing some direction, we're not going to estimate things. So let's go ahead and suppose what you might think of as the strongest assumption here, which is, under our data collection distribution, we're going to have some covariance matrix. Let's assume the features are bounded by 1. That doesn't really matter. So let's just suppose our data covariance matrices under our data collection distribution are well conditioned, so the minimal eigenvalue is 1 over d. Okay, and where does the 1 over d come from? The 1 over d is actually the best possible lower bound you could hope for, because think of like because your features are bounded by 1. Think of this these matrices as essentially 1 over d times the identity. So it's giving you the most information you can in every possible direction. So definitely not trying to cheat here. We're kind of trying to set ourselves up for success in what we might think of as the best possible situation. This is really the best possible situation for regression, right? Because we've spread out our design matrix, our linear model is correct. This would be great. Okay, so so Amin's question was like, look, how would we think about importance sampling? So, it's not like these assumptions haven't been considered. This is a really pretty standard way of thinking about this problem. So importance sampling is one way we could try to attack this. Without somehow stronger, even with these assumptions, there's nothing that goes beyond XH samples. And The thing with importance sampling is it's to a large extent, it's a bit tricky to understand how this plays well with function approximation. But practically, it's a very useful setting because you can kind of make it honest if you actually know the probabilities you sampled from. But it's very hard to deviate too much from the data collection procedure with importance sampling. Okay. But it does work quite well in many settings. And as we'll see, there's good reason to believe to try to be safe in what we do. Okay, so I'll leave this to maybe time, maybe a little later. So there is some work on stronger assumptions with regard to policy completeness. So you can replace assumption 1 with much stronger conditions on the way the world behaves, and then we can succeed. But I'm starting with assumption 1 because like this is the obvious thing to consider because your linear model is correct on your policies. Okay, and there are stronger conditions you can place on the dynamics of the world, which we know will work for upper bounds. But part of this question about statistical limits is we would like to know what are necessary conditions to succeed. Like, do we need to make stronger assumptions on the world to succeed? Or what will happen if our kind of supervised assumptions are going to work? Okay, so what's the hope here? We're trying to avoid this 2 to the h sample size. Assumption 1 has given us realizability, our features are good. Assumption 2, we're basically assuming in every slice in this game, we've got this nice well-conditioned covariance matrix. And while we're considering all possible algorithms, because we're interested in information theoretic results here, it's worthwhile in our heads to think about what's going to happen with this backward induction procedure. Because we've said under these assumptions that the last stage is totally fine. Right? That's what we set up at the beginning. We're all on the same page here. Regression is great. The last stage is fine. I'm going to take my regression estimate, plug into one step before. I'm going to keep doing this. And will this work? Again, more generally, will anything work here information theoretically? Okay, so this is the first question. Like, are we given some conditions? Are they sufficient to do sample efficient reinforcement learning? Okay, so let's take any offline algorithm. So this is something that we'll actually let the algorithm know the distribution mu as well. So the algorithm knows the data collection distribution. It knows it has a particular policy in mind it wants to evaluate. It knows the entire feature mapping. So there's no computational restrictions to this algorithm. It can see this gigantic table of features, which could be infinite or exponentially large. Okay. Now we have a pretty unfortunate result that under these 2 assumptions, so we have coverage, there's going to exist an MDP such that for any policy, not just one of them, for any policy, this algorithm is going to require d to the h samples to output the value of this policy up to constant additive error. So this is a setting like, look, every policy has a linear value, and we cannot estimate a single one of them. Okay, this is very different from the h equals 1 case. Okay, so let's try to get some intuition for what's going on and ask the question of like, okay, look, lower bounds, is something pathological going on here? Is this just going to work in practice? Because people are going to try to do things. So it seems like a pretty basic question to address, particularly in these high stakes applications where, electronic medical records, we're going to be trying to do things. So we want to pin down what's going on here. Like, is this some pathological example? Okay, so first, some comments here. We see that we already see that this offline problem is much harder than the h equals 1, because at h equals 1, everything's fine. Okay, but when h is bigger than 1, we start exploding. So there really is an exponential separation between offline RL when h is bigger than 1 versus h equals 1. We can consider that particular least squares policy evaluation algorithm. So this is that algorithm we looked at before, which is we just do least squares with bound and backups. And what's pretty surprising here is if you think about it, you're actually getting an unbiased estimator with this algorithm, because at every step you're getting an unbiased estimate, and you're plugging an unbiased estimate into something else that's unbiased. And by the Tower property of conditional expectation, you're getting an unbiased estimator with this algorithm. But it's actually going to have an exponential variance, even with this well-conditioned matrices. And what's interesting about the construction, I won't go into the details of the construction in particular, is you actually don't need many states and actions. Like the number of states and actions in our construction is order the dimension of the problem times the number horizon, and there's only 2 actions. So this is a problem where if we had an online problem, this would be easy. It's not like 2 to the h states. Like online, this would be completely trivial. Okay, but the offline problem is really quite hard. And I think what's interesting here is we're starting to see why we get this geometric amplification in RL, even with well-specified models. Like we know in practice with misspecified models, bad things can happen. But what's kind of interesting here is in the well-specified case, things break. So I'll wrap up in about 5 minutes, and I think that'll leave us with about 5 minutes of questions because we started here late. So we can look and try to see what happens with our error analysis, okay? Because let's just consider a case where a sampling matrix is the identity at every level. That's 1 over d times the identity. Because just by usual regression, our estimate of the weight vector at the last stage is d over n. In square law. So under the data norm, it's d over n. This is just vanilla regression. And that means in Euclidean distance under the data norm, it's root d over n. Okay, our q versus q hat, well, that's just our error in the weight vector. So at the last stage, this is literally the regression guarantee we had at the start. You know, our error uniformly at the very last stage, so that little h should be capital H, is basically the 2 norm of the weight vector, which is actually very accurate because our regression was good. But we pay an amplification of root d because we're translating from the 2 norm, we're going to the 2 norm from our data norm. Okay? And our data norm is well conditioned, but we do pay a root d factor there. Okay? Again, this is just what goes wrong in an upper bound analysis. Okay? I'm not going to spend too many details, but you can just try to take this guarantee, shove this into 1 level up, you see an amplification effect. And then you have to ask, like, look, every time we do this in analysis, we are wondering, like, is there slop in the analysis? And, you know, in this case, like the lower bound shows there isn't. We'd like to understand the generic, because if you look at this analysis, this doesn't actually happen in the racing example. And a lot of examples you might think of, this sort of amplification isn't occurring. Okay, so let's actually just look at a simulation here to try to see if we're getting this style of amplification. Right, so this is an amplification where, you know, just as homework, just go through to see what happens when you take your regression guarantee. You're going to plug that into 1 stage before. You're going to see how at least some way of doing the triangles is going to lead to some type of amplification. You're going to be wondering, like, hey, is this real? And those of you who studied RL, you know it's not real in some cases, like this tabular case with the racing example. Okay, so, and while this is information theoretic, we're really, because of the way we're doing these things in practical in practice, we kind of want to know, is there a sense in which this is also generic, not just some like pathological example. And when we were working on this, we started doing simulations to try to see, you know, how bad is the situation? Because we know, like, that analysis, that sketch I sort of breezed through, if we were in this racing example, so these phi's are the standard basis vectors, there's no error amplification. So this is a totally bogus analysis. So let's consider another example, which is the simplest thing you might try. Make some random features. So it's literally a tree that looks like this. And the dynamics are deterministic. So think of this as actually like the state of the world. There's there's going to be some number of actions. The dynamics are deterministic. So there's no randomness coming from there. We make our features to be random, positive vectors, and we normalize them. We're going to forget about even a sampling distribution, make life even easier. We plant a standard basis at every level, and we just literally take the uniform measure on the standard basis. So this is fixed design. There's no sampling error at all in where we get the features. We literally just take the standard basis. Everything's normalized, it's spread out. We make random weights in this tree. We just plant the rewards in there, so it's completely consistent. All the rewards are going to be bounded between -1 and 1. So it's almost like the simplest example we can think of. it's deterministic, it's realizable for this given policy, and now we just run the experiment to see what happens. And if we think about, let's put our computer science hats on rather than our statisticians hats on for a moment. If there's no noise in the system, because as of now, the dynamics are deterministic. So if the rewards were deterministic, we're literally just solving a well-conditioned, consistent linear system at the last stage. We plug that into one step before, we're solving a well-conditioned, consistent linear system, and everything would work if the rewards were deterministic. Okay, because this is just a sequence of well-conditioned, consistent linear systems. We don't even have numerical problems here. So this is completely trivial with a deterministic transition, deterministic rewards. We don't have to see everything. Now, at the very last stage, we're going to add 10 to the minus 10 reward. So that's going to be the standard deviation of the reward at the very last stage. So it's, if we think about a numerical linear algebra, you can think about it, we're just solving this backward induction procedure with a bit of noise. I mean, it is a statistics question, but it looks just like some numerical linear algebra problem where we're introducing a little bit of noise at the very last stage, and everything after that is deterministic. We're not adding any more noise to this procedure. And let's not worry about other algorithms here, information theoretically. Let's actually just look at this backward induction procedure because it is the obvious thing to try, and it's horrible. Okay, so so capital H is the last stage because we're doing 100 levels. So at the very last stage, yeah, it's super low error as expected because it's, it's basically, it's almost a numerical problem. Okay, and we don't have to worry about and we have the well-conditioned basis at every level, right? So our sampling matrix is literally the identity matrix. Okay, and it's 10 to the minus 10 error, and you're exploding. Okay, this seems just horrible. And in this particular case, sure, it's not information theoretic because there might be other algorithms that work, but it is the kind of obvious thing we're going to try. And our theorem already showed that information theoretically it wasn't doable, but this is really giving us more evidence that this type of amplification might be quite generic. Because turn off this reward and you've got well-conditioned, consistent linear systems, everything works nicely. Okay, and I think, I'm just going to end in a moment on, what are the implications of this for practice and how we think about this? See, at H equals 1, in practice, the real problems are model misspecification and sampling bias. Like everyone, if we put on our empirical economist hats or the statistician's hats, all of stats, not all of stats, but a lot of empirical stats and empirical economics is because our model is not correct and our sampling biases are wrong. Because if they were correct at H equals 1, we're done. H equals 1 is super easy. Okay, what's really bothersome here is that the situation is much, much worse. In the best case scenario where our model is correct and we don't have these sampling biases, we get this amplification. So it's obviously going to be compounded in practice by the fact that, look, in these EMR settings, we obviously have model misspecification. We clearly have sampling biases in how the treatments occur. And a lot of the concern is how we mitigate those aspects of things. Okay, and this is worse because we don't have to mitigate those aspects because I assume things are correct. And everything still falls apart. And we see this geometric error amplification. And there's reason to believe it's generic. Okay, so given the time constraints, you can just go ahead and look at the paper for the upper bounds when things would work under stronger assumptions. But what we basically showed is under kind of the two most natural assumptions we could hope for, we still see this error amplification, and it's information theoretic. Okay, and from a theoretical perspective, it means we need much stronger conditions. I think the practical impact is quite substantial because look at H equals 1, all the concerns we have, as I mentioned, is about the model being incorrect, sampling bias and such. Okay, but here it's a much worse situation because when those situations are addressed, we're getting error amplification even in the settings where we have good features under this realizability condition and coverage. So we really have to think quite carefully about how we do this offline sequential decision making. and what the quality of the features are. And this is joint work with Dean Foster, a statistician and good friend of mine, and a recent collaborator, Rusong Wang, who's an upcoming student, really doing a wonderful work in the theory of reinforcement learning. And we've been trying to understand, what constitutes good representations in RL, essentially for offline and online problems. So thank you very much.
Thank you so much, Sham. Really enjoyed the talk. So in the interest of time, I think we should, I have a lot of questions, but I think I'll wait for the Q&A session. There was one question in the chat that I wanted to relay, just a quick question. They asked, basically, in healthcare, we may focus on the patient survival, which is a survival function of many vital signs, longitudinal and other biomarkers. How does the reward like the survival time fit to the current framework?
Yeah, so you would want to modify, if I understand the question, so the question is about you're looking at the survival time.
Right.
Yeah, okay, so if it's a time, you could just say the reward is the duration. You're going to have to consider a real valued signal. It will fit in the current framework because here's a setting, this is a common setting where we put the reward at the very end. So in the examples I showed you, there's intermediate rewards, but you can easily get these these hard cases where the reward is at the end, and you can make it generic. So you might have to change the model to be a logistic model, but in a sense, from the lower bound perspective, the fact that this is bad and it looks generic really does mean, like in these healthcare scenarios, you want to be very cautious. And I think the take home is once we start looking at upper bounds, I would trust things in healthcare settings only when the policy to be evaluated has somehow some kind of low distribution shift to the data collection. But there's many, on top of all the things you already know about for why you should be cautious, I'm adding another one to make your life harder. So sorry about that, but that's basically the short summary. I just made everyone's life harder, or at least Rusong has, by saying all the things you thought were bad, well, it's even worse.
Great. Thank you so much, Sham. And the link for the Q&A is in the chat, and we'll see you again at 2:50.
Yeah, I'll take more questions then. Thank you.
Wonderful. It's my pleasure to introduce the next plenary talk. I suppose we stay on the West Coast earlier in the day. So it's my real pleasure to introduce Professor Gianluca Iaccarino from Stanford University. He's a professor in mechanical engineering there, and he is the director of the Institute for Computational Mathematical Engineering. He received his PhD from Politecnico di Bari in Italy, spent some years at the Center for Turbulence Research, and before he joined the faculty there in 2007. Gianluca is an expert in high-performance computing. He's done influential work on uncertainty quantification, engineering turbulence simulations and modeling, and data-driven modeling. He's a recipient of numerous awards, including a PCASE award in 2010. He's a fellow of the APS, the American Physical Society, and serves as associate editor for a number of influential journals, such as the Journal of Computational Physics. So today we're just delighted that he's joining us to present his lecture entitled Engineering Simulations in the Age of Data. Gianluca.
Well, thank you very much for the introduction, Charles. I hope you can hear me well.
Yes.
So thank you for having me, and I enjoyed the talks so far. My presentation is going to be a little bit different, perhaps, from some of the prior ones. I'm going to be focusing on using data science tools in an area that has actually been quite mature in terms of simulation and engineering for quite a while. So obviously, the sort of direction in which my talk will go is a little bit different than some of these new unexplored areas. So let me start by setting the stage by acknowledging that data is everywhere. And when I say this, I do want to characterize it with sort of starting from the most obvious. We do have data acquisition platforms that are generating an enormous amount of data around us, regarding all aspects of our life. But it turns out in an engineering setting, physical sensors are becoming similarly more and more powerful and more able to generate, collect and store data, collect information. And so we have a richness of sort of characterization of our engineering devices that has grown exponentially in the last few years. And then in addition, we have been very, very effective at creating data both in lab settings, so very, very controlled environments, but also through very detailed simulation. So data is everywhere, especially and also in engineering setting, I would say. The next question is if data is everything. And in that respect, I do acknowledge the fact that over the last 10 years or so, there has been a sort of an interest in resetting sort of the stage for everything we do in science and engineering. And in some cases with some extremely extreme viewpoints in a sense. So I have a couple of examples here. I'm not going to go in details, but the idea is that the presence and the ability to digest and manage a tremendous amount of data might actually provide a completely different paradigm for this and for science and engineering. And in many ways, we're seeing a number of conventional disciplines or standard disciplines that have been affected and somehow sort of digested, if you like, within data science in one of its forms. And so one of the questions that I pose myself and I want to discuss with you a little bit is the fact that sort of engineering simulation seems to be sort of there for the taking. And the question is how quickly can that happen? The other part of my title was the idea of age of data. And I do want to acknowledge the fact that we already talked about data and the fact that data is more and more available. And so certainly that is one characterization of why this is the age of data. But I would say there is more to it. And in some sense, actually, there are two additional elements that are more important than just the fact that data is available. And the two are the fact that we do have software that is professionally developed, open source, very effective, very easy to use, that is, readily available today. And many of the speakers have talked about how their particular algorithms and ideas are implemented in a way that becomes extremely easy to use. And then the next is that we have computing for data. And again, very dedicated new type of hardware that makes the management, the digestion, the analysis of data much more and more efficient as we move forward. So in that sense, I do see that the age of data is the combination of these three factors. It's not just the data. And in that sense, we are certainly in this new environment for these reasons. Now, interesting enough, there are a number of applications that fit into that framework quite nicely, very, very effectively. And I have just a few examples there, but in our life, we are surrounded by application of machine learning and artificial intelligence that are already very, very mature and very effective. So there is no question that in a sense, there are success stories out there that we need to acknowledge, and obviously we acknowledge in our own lives. So the question is now how this connects to engineering simulation. So let's go back there for a moment. And these are some of the engineering simulation I'm interested in. I had movies for all these, but I decided to skip them. My internet connection is a little bit sloppy at this point. But the examples here are just three from sort of my past projects. And they indicate a couple of things. First of all, the fact that we are interested in some cases, in extreme complexity of our devices, engineering devices. This is on the left, you see a jet engine, and the questions there have to do with emissions and how we can design systems that comply with the emission requirements that the world is asking us to comply to. Noise is very similar. That's the top example there is the sort of exit part of a jet engine. But on the right-hand side, I have an example that is more on the biomedical side. And the question is if we can devise, in this case, aerosol devices that can actually be more effective for treating patients. So what I would sort of characterize this example with is the fact that these are simulations that address very high consequence decisions that we can make either as designers of engineering devices. Say a jet engine development is a various $1 billion investment. So obviously our simulation help us manage those risks and those decisions we make. In the biomedical application, obviously the decisions are even more directly impacting individual patients. And so obviously those decisions, again, are very high consequence. And so I would characterize what I'm interested in is really engineering simulation for applications that have very, very low tolerance for mistakes, for errors. And I would say probably for everybody would characterize those simulations with that sentence. But in my talk, I'll try to sort of drive to the idea that these high consequence decisions, this sort of low level of tolerance for error is actually a critical element for what we do. So just to give you a very high level view of what engineering simulations are and how we actually arrive to the type of simulation that I showed you, it's very interesting to think of the fact that we do start typically from data and prior knowledge. That's what we know about the problems we are trying to solve. And in this case, data is not necessarily a very extensive set, but certainly observational data is where we start. Typically, we formulate physical principle, or we try to understand, based on the observation, what is at play from a physical perspective. And in many ways, we call those first principles because these are the simplest sort of building block of our understanding of reality, of the systems around us. From there, we build mathematical models. We deal with extreme simplifications because these models tend to be incredibly complex. We translate them in our computer codes that allow us to translate those ideas, mathematical ideas, into solutions. Because again, typically we cannot solve these problems directly. And then we use supercomputers to actually perform those simulations. And again, the goal is sort of inform these high consequence decisions. So the question mark is is there a different paradigm at this point? This is what I described at very high level is a sort of conventional, very well established paradigm. So the example that I want to take is very well known, is the idea of using, in this case, machine learning strategies to build human-like faces, synthetic faces in this case. And the strategy behind them, again, is something that is very readily available. We can actually build databases of real images, train our tools on those. The specific of what machine learning tool we use is actually not very important. And interestingly enough, every one of these on Google Cloud use different detail methods to accomplish that. But more importantly, the process is always the same. You have a database of images in this case, and you build a predictor that creates actually a new image based on certain characteristics. And so what we asked ourselves, can we do the same with flow simulation? Can we do synthetic flow simulation? We have a battery of real flow simulations. We build a database, we train a network, some sort of machine learning tool, and we generate new ones. And so we did exactly that. This was a very, very simple case, just as an illustration. So we built, thousands of simulations. What you see on the first column is the geometry. So in this case, we have these sort of circles, squares, triangles, and so on. The next column is what the flow field will look like. In this case, the velocity magnitude. Velocity is low in the red region and high in the blue region. And out of these 1,000, we build a machine learning system. In this case, it's not too important, the details, which with the idea that you are now able to, once this is trained, you are able to input a new geometry. So just the geometry, the description of the parallelepiped, block or whatever polygon you want, and it gives you in output the velocity field. So does this work? Well, actually, this is an example of an unseen input, the predicted output with machine learning, and the true solution. And even just at the naked eye, looks very good. If you do more precise error analysis, you see that actually the error is pretty low, less than 1% on hundreds of unseen geometries. And more importantly, we were able to generate these 100 solutions in nothing, less than a minute on a laptop, which is obviously, you know, not something that will be easily available to full-blown simulations. So it seems like end of the story. Yes, this works. Well, it turns out there are some challenges. Building the data set is extremely expensive. So these thousands of simulations are simple in this case because the simple two-dimensional setting, just, you know, polygon geometries and so on, but it's not quite straightforward. Training the network is also expensive, and it does really require a number of characteristics that are sort of outside the scope of typical knowledge in the simulation world. So you need to bring new expertise. But the other more concerning is that the prediction accuracy is really measured in average. So the idea is that you are understanding of what the accuracy is by doing many different tests and perhaps different geometries. But the truth is, if I give you one particular geometry and only one, and I want to know what is the accuracy, well, it turns out in some cases the error can be fairly high as even 5% in certain locations. So although sort of even this case at the naked eye looks very good, in practice is actually potentially quite inaccurate, beyond sort of the accuracy that you can expect. And it's particularly challenged to understand what you do next. If that 5% is not satisfactory, what is the next step? Do I build a bigger data set? Do I change my training? What is that you do? And this is part of the difference in between sort of the classical engineering simulation, in which we have very clear understanding of where the accuracy limitation might come from, and in this setting where obviously is a very different strategy and requires very different expertise, but there is not an obvious connection one-to-one. Now, the second real problem has to do with generalization. So we trained our models to be able to distinguish geometries that look like these, polygons. So what happens if our geometry now has multiple polygons? This is very common in engineering, and from a simulation perspective, it is harder to do those simulations, but you don't change the first principles. They're exactly the same. So what happens in this setting? And so it turns out that if you train only on single body geometries and you try this sort of more complex setting, turns out, again, at the naked eye, things look very realistic. And so this was quite a surprise for us, and quite interesting to see that actually the overall learning, even if we never contemplated multiple bodies, was actually able to display some interesting characteristics, which actually compare relatively well with the true solutions. So these are true solutions, the third column. And you can see there are differences, and obviously not exactly the same, but there are sort of reasonably accurate. The error in this case, in some cases, goes up as high as 15% in this case, but still, I would say this is a pretty interesting application. But again, the challenge in this case has been, this is all sort of interesting, but is it really something that we can easily improve in terms of accuracy? Well, I want to show you just an example that tells you actually the opposite. So there was a similar work done sort of in parallel with us, using a completely different network, a completely different application. So what we wanted to do is to actually do a one-to-one comparison. That's typically what we do also with engineering simulations. And the question is, in this case, both of them are very sophisticated, use a very large number of very general construction. We are using exactly the same data set. So the only thing we are changing is basically the framework for the machine learning architecture, if you like. The software is also different, but the basis is basically the same, and you would expect a reasonable accuracy. It turns out that at the end, for a prediction case, the results are actually very different. And so if you fix the training cost, which simply means that we are using exactly the same data set for the training, both in terms of simulations and data, the accuracy is actually quite different. And this is not to say that one is much better than the other. It's to say that there is a very large sensitivity. And as you can see from these two results, it's actually quite difficult to even understand the type of errors that you're getting. So bottom line is that I would say it's interesting. It's possible to sort of jump directly and completely change the paradigm, but it's not obvious that we have sort of a very simple solution on our ends. So the other thing I wanted to point out is that I was lucky enough to have about 80 researchers in fluid mechanics in my disposal for a survey during the summer of 2018. In these COVID times, it seems amazing that we had 80 people in a room, actually. But it turns out we were able to run a survey, and there were a couple of questions. And it turns out on this very, very biased community, 80 fluid mechanics researcher, the challenges that they see in using data-driven prediction are basically the fact that we have low confidence in the final prediction. We have no real understanding of the accuracy. Obviously, we're ignoring physical principles that we've fought a lot to accomplish and to learn. And there is also this question about what is the data, what is the construction of the training set that you need to use, which are very, very interesting. They don't say too much about the machine learning or the artificial intelligence per se, but they talk of how sort of an external user will look at sort of a changing paradigm in this sense. So the point is that I think it's important that we think of our expectation a little bit differently. I think the whole idea of sort of throwing everything away and being able to start from scratch and do it very effectively might happen eventually, but there is a long way to go. So let me just change the paradigm then, and in the last 5 minutes, talk to you about how we are using it right now. And the intention is that we have to acknowledge that even our simulations that we're doing right now, even if we use supercomputers that are extremely expensive, they are not perfect. And there are a number of uncertainties that come in our predictions that we need to acknowledge anyway. And so it turns out that what are these uncertainties? This is sort of a cycle for our engineering simulation. We have inputs that we have to specify, say the geometry, the operating conditions. We perform our simulation, we get outputs. It turns out that all the characteristics that go into the inputs, say the manufacturing process introduces uncertainty, say in the geometry, that do affect the behavior of the system and eventually might invalidate our predictions. So it turns out we are able to characterize those uncertainty very nicely. I'm going to go very quickly here, just to say that for this kind of uncertainty that have to do with variability, if you have enough computational resources, you actually can do a very good job, and you can learn a lot about those effects into your predictions. But it turns out there is another source that is much harder, and has to do with those simplifications that I mentioned at the very beginning, those assumptions that we make to build our mathematical model. So even before we compute anything, we have to decide on some characterization of the physics that we can actually contemplate in our simulations. And I'm going to focus on turbulence modeling because that has been sort of my bread and butter for many, many years. But I do want to mention the fact that if you look at the annual review of fluid mechanics, 2 out of the top 5 papers that have been downloaded over the last 12 months have to do with the use of machine learning in this setting. And so it's an incredibly popular topic, and there is no way I can give credit to everybody that is working in this field. So I'm going to just take a very, very limited view and give you just one example and finish. But before moving on, I also want to point out that the 5th paper in this list is actually another paper that I wrote with a professor at JHU. So I'm very happy to acknowledge him as well. Rajat Mittal is a colleague of mine a long time. So there is still something else in addition to machine learning that is still generating interest in fluid mechanics. Okay, so I don't plan to give you a lot of details about turbulence modeling. Suffice to say that the goal is to actually build this 3x3 tensor. This is the Reynolds stress tensor, is a constitutive model, if you like, for the fluid, for a turbulent fluid. And it has some nice mathematical property that allow us to just build an eigenvalue decomposition, basically. So we can decompose that matrix into eigenvalue eigenvectors that sort of represent this ellipsoid, the shape, alignment, and size of these sort of graphical representation of the Reynolds stress. This is in a particular point of space, in space and time. So this is just a very local representation. It turns out that there is enough evidence, or there is sufficient evidence, that some of the characteristics that lead to modeling error, our turbulence models being incorrect, have to do with some of the characteristics of this decomposition, either the eigenvalues or the eigenvectors. But for the purpose of this talk, one thing you need to keep in mind is that because of the mathematical property of this object, of this Reynolds stress, again, the symmetry and the the semi-positive definiteness, you can actually imagine that there are limits into how much this ellipsoid can change. And it turns out you can nicely organize them in a triangle where the shape here is actually representing of different type of models that you could decide to build based on the evidence or whatever observations you have. And this is all. There is really nothing else that you can imagine that happens. This is the space of all the possible models. Obviously, for a given set of eigenvectors, because eigenvectors will sort of change the orientation of these ellipsoids. But it's nice to think of these as a constraint now. For any model, I could sort of think of this area, of this triangle, as a sort of a space of possible models. And I could actually build many, many models that look like the original one, but they're slightly perturbed, and try to assess if my results are sensitive, have prediction sensitivity. And this is exactly what we did. And this is a very classical case, the flow over a backstep. You see the schematic there, the flow over a backstep separates, creates a separation bubble. And what I'm showing you in the picture before, the XY plot, is the skin friction. So it sort of illustrates the separation. The solid line, the black line, is the prediction of the original model. The red symbols are the experiments, and you can see there is a very large difference. But we can actually characterize the uncertainty in our prediction, the uncertainty of the black line, with these sort of purple or bluish intervals. And this is our approach, and has been sort of kind of interesting, at least in terms of how to apply it and so on. But it sort of tells you that, yes, if you can quantify your uncertainty, you have an handle on how much error you might expect in this model. So what the next step of this is, well, this uncertainty is quite large, because we're just saying that the models can be anything, right? In this triangle, any model is possible, is realizable, as we say. But the truth is that some models are very unlikely. And we are not using any data to try to understand how to characterize these uncertainties, these variability models. And so this is where the data science part comes in. So we take a baseline model, we build a machine learning tool that tries to learn about the difference between these two. But the idea is that rather than trying to learn between the difference of the truth model, the data, and the baseline, and build a better model, what we try to do is to actually simply limit how much perturbations we need to apply to the system, right? So the idea is that we're not trying to build the perfect model out of data, because we know that's incredibly hard. But what we're trying to do is to get a sense of how much perturbations we can actually expect based on real predictions of a real specific conditions, specific flows. The details of this is not important. I just have it here because I wanted to point out something afterwards. We're doing this in OpenCV rather than in some of the more conventional or more popular tools like PyTorch and so on. Partly because, as we will see later, CFD codes or fluid mechanics code tend to be still, for a vast majority, running on CPUs. And on CPUs, some of the machine learning tools tend to be slower. They're obviously optimized on GPUs. But there are a number of other reasons why we are doing this in OpenCV. But anyway, this is just an open source collection of machine learning tool on top of other capabilities. Again, I don't think I need to explain how this strategy works. I'm just going to say that these are very preliminary results, just to give you an idea. We are using only one data set as a truth model right now. The discrepancy, as I said, is based on the distance in this eigenspace. So it's nothing to do with specific quantity of interest. It's really something you want to predict. It's really to do with the shape of these ellipsoids, if you like. We use, in this case, 13 features. We studied a variety of them, but these are a subset that we're using right now. And rather than using deep learning like the image might sort of indicate, we are using actually random tree. Oh, sorry. That's a random forest regression for our methodology. And does it work? Well, this is a very simple example. This is actually the data set we used. The left is the actual distance between the eigenspace, so the distance between the eigenvalues in this case, for within the flow field. So the flow is actually left to right. Once again, there is a flow separation from the top of the wavy wall here, and you can see that the discrepancy is higher where there is yellow, obviously in this case, and then lower in the blue region. But actually, our prediction with the machine learning, this is the regressor that we built out of the training set, actually predicts that relatively well. And you see a more quantitative comparison here. Again, this is sort of an effort in sort of showing you some results, but these are very preliminary, so I don't want to make too much of a claim here. But this is actually the final end, the final result. So the left is what we did before, just using eigenspace perturbations over the entire possible set of models. And you see that the uncertainty range is actually quite large, expectedly so, because there is a large variability of models. And many of these models are actually extremely unlikely. And so what you see on the right is what we get when we limit our perturbation. So the machine learning helps us identify those bounds, and then we apply perturbation only within those bounds. Let me just finish by showing you how this works on these. So that was a test based on the actual data set that we trained the model on. So this is an actual prediction, and this shows, again, the difference between doing this perturbation over the entire set of models or actually pushing the perturbation only to the models that are actually more likely. And it turns out that, as you can see, the bounds are much, much tighter, closer to the experiment, which is also positive. But in a sense, it's really indicating the fact that the idea of trying to use the machine learning to bound rather than to predict is actually potentially an interesting direction to go, a useful direction to go. So I want to finish with the final thought, and I showed you this plot before. So I guess you believe me in saying that I don't, or you trust me in saying that, given my experience so far, I don't think we can fit into this paradigm in terms of engineering simulation, at least not directly. There are a number of additional things that I think will be required for the whole field of engineering simulation to become much more attuned with data science. But I would say that the paradigm is actually not that different. The first is that I think physical principles have to become a first-class citizen. I think there is no way you can hope that the data that you have will be sufficiently informative to replace all that knowledge, especially might be informative, but might not, certainly not be effective. And all we know is actually very valuable. But the other important challenge that I see right now is the fact that there is a divide, both in terms of software and computing, between data and simulations. So how to bridge that divide and how to merge those two sectors is probably another challenge that we have to address. And so the idea is that there is work to do. Is very exciting. And as we move forward, I think there will be more and more opportunity to fuse data with simulations. So I had a number of pacing items here, but I think in the interest of time, I'll skip. I'll just want to say that I believe there are both short-term, sort of low-hanging fruits, but also a lot of long-term opportunities to do great work at the intersection of sort of engineering simulation and data science. And as I said, I couldn't really review the literature in this short talk, but there are a lot of really interesting ideas out there, and I'm happy to answer questions if you have any at this point. So I'll leave it at that, and thank you very much for your attention.
Thank you so much, Gianluca, for the excellent and informative presentation. It's great introduction and pointing out the challenges to kind of try to merge these two communities. Let me see if there are questions. We do have some time. I certainly have a few, but let's see. So I'm supposed to look both at the Q&A window and at the chat. I don't seem to see anything in particular here. So let me start maybe. I was fascinated by this first example you showed with the flow going over this. I guess it looked like cylinder and a few plates that had different angles. And then indeed, if now you stick 3 in there and it still seems to reproduce those wakes in the different places. That's fascinating. I was wondering, what if you change the shape of the object to something concave or convex? If you change something, or something that has like branches or something completely different. How far have you explored this sort of thing?
So we did try a star, the flow around the star, and I don't have the results here. Again, at the high level, they look very reasonable. So I think what happens is that the training model, because there's a convolution sort of built in, is able to extract some sort of local feature and try and sort of identify the fact that depending on a front face versus a back face of a geometry, there is a very different sort of scenario of what the velocity should look like. So I think it's able, even in a complex setting, is able to distinguish those features and sort of adapt to that. And I think that's what's happening with the multiple body as well. It's not really learning that there is an interaction or intersection between the two. It's really just identifying those geometrical features as being likely to dominate the flow.
Yeah, I also think for this audience, probably very interesting to hear that, you know, a few percent or 5% error is simply unacceptable. Especially, you know, if you see a jet engine, I think people will agree with that, and that does place kind of a different level of requirements on what is expected. But,
absolutely, and in addition, to complement that, it is also important that again, you have a strategy to sort of reduce that error if needed. It's not just that the error originally is large. The question is that try to reduce it is really opening up so many other opportunities or requirements that becomes really hard to sort of build a strategy to, you know, methodically reduce that error.
Yeah. Fantastic, wonderful field for research. Lots of things to do, lots of proposals to write, right? Anyway, thank you so much for joining us today. So that concludes this plenary lecture. So I do believe we are on time to continue with the program. And so I believe what we have next is the third update from the IDIES Seed Awards. I think we have Ben Haeffele on here. I think it's also Matthew Ippolito, both from Hopkins. So they're going to give their update on a project entitled Machine Learning and Computer Vision for Malaria, Disentangling the In Vivo Effects of Anti-Malarial Drugs. And with that, I don't quite know to whom of the two of you to hand it over. I'll just leave it open. You guys jump in.
Yeah, I think Matt's going to get us started.
Right.
Okay, I'm using an external monitor. So are people seeing the presenter mode, or are they seeing the actual? You're seeing the actual presentation.
Yes,
okay.
It's good.
All right. Yeah, so I'm Matt Ippolito. I'm joining from the School of Medicine and the Johns Hopkins Malaria Research Institute. And as soon as I move over this window, panelists and see my slides. Okay. And so for the next 15 minutes or so, Ben and I will tell you about our project, Machine Learning and Computer Vision for Malaria. And first, I would like to thank the School of Engineering and support from IDEIES, without whom none of this work would have been possible at all. And second, I would like to mention some historical trivia that much of Johns Hopkins' storied history as a research institute actually has its roots in malaria, including anti-malarial drug development back during World War II, but has been largely forgotten since malaria was eliminated from the United States just in the 1950s. So I'll present part one, which is an introduction to malaria and how data science can impact malaria research. And Ben will present part two, which provides an overview and progress update of the machine learning-based computer vision algorithms that he's been developing along with Kevin Tran. So malaria is a parasitic infectious disease that is preventable and treatable, yet a child dies from it every minute, mainly affecting tropical areas in sub-Saharan Africa and South Asia and Southeast Asia. The parasites have a complex life cycle shown at the bottom of your screen that makes radical treatment elusive. And what I mean by radical is the ability of a particular drug to clear infection from all parasite stages. Our work takes place in a larger context of the global spread of multi-drug resistant malaria, which makes the need for new effective treatments urgent. The key point of our work is that drug development for malaria requires understanding how different drugs impact different parasite life stages. However, in clinical trials, this is not routinely done. In fact, it's almost never done because of the limitations of current methods, which rely on highly trained laboratory technicians examining thousands of parasites, which measure only 10 to 20 microns across under the microscope. So anti-malarial drug efficacy then is therefore a function of the parasite stage distribution, since different stages vary in their susceptibility to drugs. Some stages are intrinsically resistant to existing drugs at the same time that other stages of the parasite are exquisitely sensitive, but unless we look, we're unable to differentiate. Malaria is one of the few infectious diseases that can be fatal within 24 hours of the first appearance of symptoms. And here on the left, I'm showing you a zoomed in portion of the parasite life cycle, and I'm highlighting the stages of the parasite that are responsible for clinical illness that we can see under the microscope. In the middle, I've illustrated 3 possible scenarios for where in its life cycle the malaria parasite is situated at the moment that treatment is started. So in the first scenario, the majority of parasites are in their early stages, which tend to be less susceptible to existing drugs. And as you move to the right, the parasites become more mature and more susceptible to our current drug options. And then on the right is actual clinical trial data, the first ever trial that I'm aware of to start to look at the different parasite stages. And it shows different degrees of drug effect based on the distribution of the parasites at the time that treatment is initiated. These sorts of data are very important for identifying optimal therapies during the drug development and drug optimization phases, while they also have implications for how we detect and respond to anti-malarial drug resistance in the field. And that has enormous public health implications. So what's almost unique to malaria is that a biopsy is as simple as a prick of the finger, where every drop of blood can have tens of thousands of parasites at different stages and therefore different levels of drug susceptibility. But as I just mentioned, current methods rely on routine microscopy, which we believe is incapable of extracting all of the clinically important information that each blood slide biopsy holds. So now I'll turn it over to Ben, who will describe the machine learning and computer vision algorithms that his lab has developed.
Great. Yeah, can you just go to the next slide, Matt? Great. Yeah, so from a computer vision standpoint, you know, we're going to have these images of blood cells taken under a microscope, and there's essentially 3 sort of primary computer vision problems that we want to solve for this project. The first is really just let's detect all the cells in the image. Then once we've detected all the cells, we really want to do sort of a first classification just as to whether that cell has a parasite or no parasite, fairly straightforward binary. And then after we've identified all the parasites, as Matt was alluding to, you know, there's a lot of potential value in the information about what life stage these parasites are in. So once we've detected the parasite, then the final thing we'd like to do is really classify the life stage of all these parasites. For example, say this is an immature trophozoite. Go to the next slide. Yeah. And so for those of you that work in computer vision, you know, you'll probably recognize that these are fairly well-studied problems in computer vision, you know, things like object detection, image classification, etc. But compared to sort of a typical computer vision task, there's a few sort of challenges that are unique to this project or biomedical data in general. And the first is that, you know, most state-of-the-art computer vision object detection algorithms, for example, are built using very heavily annotated training data sets. So for example, if you have an image of a street scene like this, essentially all the objects in this scene have been annotated by drawing a bounding box around the object. Likewise, each bounding box comes with a label as to what's inside that object, a person, a bicycle, a building, etc. And then likewise, a lot of these algorithms are designed to really work with relatively small images. So images are typically downsampled to be maybe a few hundred pixels in each dimension. Next slide. And so if you contrast biomedical applications or this application in particular, you know, some of the challenges you run into are that, you know, usually you're lacking in annotation. And so you know, you essentially have this image on the left showing, you know, a drop of blood image under a microscope, but you have no information about where the cells are in this image. Likewise, you don't know where the parasites are in this image. And additionally, you know, if we're interested in classifying the parasite life, also don't have information about that. Beyond that, these are very, very large images. So those of you that work in areas like digital pathology will probably be familiar with this issue, but these images have billions of pixels in them. You know, a single image can have millions of cells in it, corresponding to, you know, potentially hundreds of thousands of parasites in a single image. And so this presents challenges from a computer vision aspect. And so to address these challenges, we don't necessarily have to start entirely from scratch. There are some existing data sets that we can take advantage of. And so as one example, there is sort of a curated data set from the NIH where you have these sort of tightly cropped images of cells under a microscope, both with and without parasites, and they've been labeled. And so this, gives you a starting point to do this sort of binary classification task. Is just, given a cropped image of a cell, does the cell have a parasite? Yes or no? But as you can see, there are some differences in both resolution and image statistics compared to our images. There's some color differences. Likewise, the background has been removed from these NIH training data. But nevertheless, we think we have some techniques that can address these issues fairly well. But then the next problem you run into is that we don't necessarily know where the cells and correspondingly the parasites are in these images. And so our proposed approach to do that is to work with a method known as convolutional sparse encoding. And so this has the advantage that it's largely an unsupervised method. And so we don't need detailed annotations as to the location of each and every cell or parasite in one of these images. This works really just with a and nothing else. And this leverages some of our existing work between myself and Renee Vidal and others on detecting blood cells in microscopic images under sort of a different imaging modality. But the way this method works is essentially given an input image, you're going to approximate that input image as a sum of convolutions between dictionary templates, which you can envision as just being small, 10 by 10 or maybe 20 by 20 pixel patches of an image. And you're going to convolve those dictionary templates with a sparse encoding, which is itself also a two-dimensional image, but it's been regularized to be sparse. And so these two-dimensional encoding images are essentially zero almost everywhere except for a few sort of spikes at a small number of locations within the image. And ideally, if you can solve this approximation well, then those spikes correspond largely to where your objects of interest are. So for example, if your dictionary templates are largely small patches that look like the parasite, spikes would sort of correspond to where the parasites are in the image as is depicted here. Likewise, if your dictionary templates are more looking like the entire cell, then the spikes would correspond to essentially where the cells are located within the image. And so the final sort of proposed approach and innovation that we need for this project is really how we're going to get the parasite life stage information. And so, as I mentioned, short of someone going through and sort of manually labeling all these parasites and what life stage they're in, which is extremely tedious, we're instead proposing a way to somewhat automate that approach. And this is actually through what's known as synchronized cell culturing techniques. And so as Matt mentioned, the parasites go through an entire life cycle in roughly 48 hours. And so what we've done is we've essentially infected all of these red blood cells at the same exact time, and then imaged them at regular intervals in sort of a cell culture setting. And so then, because we know how long it's been since these parasites have been infected, we can therefore assume that the vast majority of parasites that are detected in a given image will be sort of within a known life stage. And so essentially, we're planning to use this approach to sort of do automated generation of life stage information for training algorithms. All right, and so I'll just fairly briefly show some somewhat preliminary results and status. Up here on the top left, this is a small crop from one of our images, and you can see all these green dots are essentially where the convolutional sparse encoding algorithm has identified a cell center. And so, if you look closely, you can find a few errors that it makes, but by and large, I think it's doing a fairly reasonable job, especially considering that this is an entirely unsupervised method. There's nothing to train here. It's really just defining a few templates, and then it runs entirely unsupervised after that. After we've detected the cells, then we can just sort of take a crop of that cell and then pass it into a neural network that we've trained using this NIH data set that I mentioned previously. And then if we do that, and then if we sort of manually label those detected cells as either containing parasite or not containing parasite, just to construct sort of a little preliminary test set, we're achieving roughly 87, 88% accuracy in these preliminary experiments. And so we think that's promising. We're happy that our initial sort of proposed approach is showing potential. We think there's many potential ways to improve this still. And of course, we have a lot more work in terms of validating and really testing this on a larger scale. And then also moving forward, you know, unfortunately, we got a little bit delayed in getting this project off the ground due to the COVID pandemic, but we have acquired the samples now for doing this sort of synchronized life stage training. And so we're really getting ready to ramp up our work on moving on the sort of last stage of the computer vision project in terms of classifying the life stage of the parasites in these images.
All right. Thanks, Matt and Ben. Very good for the update. We do have a few minutes if there are any questions. I'll be monitoring here the Q&A. I don't think I see too much. So, but you know, while people might be thinking about questions, let me just announce that this is then the next item is going to be the break as well as the breakout sessions, and there's two. One is on Marcy by Jaime Convarisa, and the other one on a Q&A for the invited talk we had by Sham Kakade, which is also going to be, I think the links are provided in the chat, right? So, and I believe if you click there, you need to leave this one. But anyway, with that, hoping that people will be able to participate in the chats and then come back after the break for the 3:35 last, the Minds Plenary. With that, let me close this session and wish you a good afternoon.